Welcome, everyone. Let's just jump right in, shall we? Today on The Explainer, we're digging into a literal cosmic detective story, and we're doing it by looking at a completely fascinating celestial body called the Asteroid Ryugu. Basically, scientists stumbled onto a massive puzzle here, one that totally threw their expectations out the window. It really forces us to look at our solar system as this wild, dynamic place. So, we're going to break down the clues, analyze the evidence, and figure out exactly what happened to this giant space rock.
Okay, Section 1. Unexpected discovery, gathering the evidence. Every good mystery needs solid evidence, right? But getting it from deep space? That is no small feat.
Consider this incredible machine. It's the Japanese Space Agency's Hayabusa 2 probe, cruising up to Ryugu back in 2018. Now, Hayabusa 2 didn't just snap a few photos from a distance. Oh no. It pulled off this incredibly daring maneuver to briefly touch down, grab physical samples right off the asteroid's surface, and then haul those tiny rock fragments millions of miles back to Earth. And here's the kicker. When scientists finally popped open that pristine little capsule to examine the space rocks inside, they didn't just find some boring ancient dust. They found a glaring, completely unexpected scientific mystery, literally sitting right on the surface of those fragments.
Which leads us straight to the central question for today's explainer. How did a 1,000-year-old cosmic event leave a trace we can still see today? I mean, to you and me, 1,000 years feels like forever, right? That's back in the Middle Ages. But on a geological or, a cosmic scale, 1,000 years is literally a blink of an eye. It happened practically yesterday. Finding proof of an event this recent on an ancient celestial body is insanely rare. And as you're about to see, the specific clue that tipped off the scientists, it really shouldn't have been there at all.
That specific clue is exactly what we're covering in Section 2, the sodium anomaly, a cosmic contradiction. This is where the physics of our solar system kind of seem to break their own rules.
The absolute heart of this mystery is that researchers found a literal film of sodium coating the surface of the Ryugu fragments. And we are talking incredibly thin here, just a few nanometers thick. But here's the major problem. It's essentially a locked room mystery, but in space. See, sodium is a volatile element. Out in the harsh environment of deep space, it's supposed to get completely obliterated or dispersed by the solar wind, which is that constant, raging stream of charged particles blasting out from our sun. Ernesto Palamba, a brilliant researcher from the Italian National Institute for Astrophysics, actually hit the nail on the head with this. He pointed out that under the relentless beating of the solar wind, this sodium should have vanished a long time ago. So the simple fact that it's still sitting there, it means whatever deposited that sodium must have happened incredibly recently.
To figure out exactly what left that sodium behind, the team had to zoom way in. Let's head to Section 3, Microscopic Evidence, looking closer, and see how this case really comes together.
These scientists broke out some unbelievably advanced analytical tech to study layers literally nanometers thin across two specific little chunks of Ryugu. And wow, the clues they found were wild. Yes, they found that impossible sodium layer we just talked about, but they also found these tiny, microscopic impact craters absolutely peppering the surface. And right inside and around those craters, glassy structures. Now, glass in space forms under sudden, immense heat. On top of all that, they noticed the rock was enriched with iron, which is a classic telltale sign of further weathering from the solar wind. So when you piece all these clues together, it paints a really violent picture. We aren't just looking at random chemicals. These are the literal scars of an intense cosmic bombardment.
And when the researchers finally crunched the numbers, looking at the chemical decay and the solar wind exposure, they landed on a completely stunning figure: 1,000. The hard evidence proves that Ryugu flew straight through a dense, chaotic swarm of micrometeorites a mere 1,000 years ago. It got completely sandblasted by high-speed cosmic dust. That's what gouged out those microcraters, flash-melted the rock into glass, and splattered that fleeting thin layer of sodium that the solar wind just hasn't had the time to scrub away yet.
So why does all of this matter to us down here? Let's zoom out a bit for Section 4, Earth versus Ryugu. A stark contrast, to put this whole micrometeorite swarm thing into perspective.
It really is a tale of two entirely different environments. Space is a highly active place, right? Near-Earth asteroids are regularly getting pelted by these swarms of meteoroids. But what happens next depends entirely on where you happen to be. Here on Earth, we're wrapped up in a nice, thick, protective atmosphere. When our planet plows through a dense cloud of micrometeorites, the friction just burns them right up. We don't get physically scarred. Instead, we get to go out in August, set up a lawn chair, and watch spectacular light shows like the Perseid meteor shower. We get shooting stars. But Ryugu? Ryugu has zero atmosphere, none whatsoever. It's just sitting out there completely naked to the vacuum of space. So when it hits a meteor swarm, there's no pretty light show. It's just direct, violent physical and chemical collisions that permanently scar the asteroid's surface.
Knowing all this opens up a whole new avenue of research. Let's move into Section 5, the next steps, reproducing impacts, to see exactly what the scientific community is doing with this groundbreaking data, which was recently published in the prestigious astrophysical journal Letters. The investigation definitely doesn't end just because we cracked the sodium mystery. The next major step is to take all these incredible observations and actually try to reproduce them right here on Earth in a lab setting. Scientists are gearing up to simulate these exact conditions, literally firing high-speed particles at rock samples to see if they can recreate those glassy structures, that iron enrichment, and the sodium deposition. By doing this, they're hoping to build a highly precise model of exactly how micrometeorites mechanically and chemically chew up the surfaces of small celestial bodies all across our solar system.
Which leaves us with this final, kind of mind-blowing thought. We so often picture space as this cold, static, unchanging void. But the story of Ryugu proves that it's actually an incredibly dynamic, chaotic shooting gallery. I mean, if a massive ancient rock like an asteroid can have its chemical makeup drastically altered by a violent event just 1,000 years ago, an event we literally only caught because of a sodium layer a few nanometers thick, what other wild, dynamic secrets is our solar system hiding right now, just waiting for us to look close enough? Definitely something to think about the next time you look up at a shooting star. Thanks so much for joining me on this explainer, and keep your curiosity alive.